Good morning, everyone. Thank you for joining our session. My name is Rahul Mehrotra, and I'm a product manager at Microsoft Research Montreal. Previously known as Maluba, we were recently acquired, or over a year ago, acquired by Microsoft for our work in deep learning and reinforcement learning. So today we're going to talk to you about reinforcement learning, some of the work we do there, and then my colleague Tavian Barnes will talk to you about hybrid reward architecture, an algorithm that we use to beat the game of Miss Pacman that was previously unbeaten. So what is reinforcement learning? Reinforcement learning is a data-driven approach to learning behavior. And the agent learns this behavior by interacting with its environment. Over here, I have a high-level representation of the model where you have an agent and the environment. The agent takes an action within its environment, and the environment observes that action and responds back with, what happened in the environment, an update in the state, as well as a reward for the agent. And that reward is really based on how good of an action was it that the agent took. If it's a good action, then it gets a higher reward. And if it's a bad action, it can lead to a 0 reward or a negative reward. And the problem here, and the goal of the agent is to really figure out how can it get both short-term rewards and long-term rewards. So its goal is to optimize to maximize its reward as much as possible. And this becomes really challenging because the agent has to figure out, well, should I continue to explore and take actions that could lead to a higher reward? Or do I continue to take actions that I know will guarantee me a short-term reward, but then doesn't really optimize for the overall reward it can achieve? So this is a really, really challenging problem in reinforcement learning. And if we can solve that, or when we solve that, then you can build some really cool applications and products on top of it. So for a couple of examples I thought of, we can really make an advanced proactive Cortana that learns from its environment, from its behavior by interacting with the user, and you can really customize it. It can get reward back from the user either by completing a task successfully or through verbal commands that the user might give back to the agent. You can also build really realistic NPCs or non-player characters in games where these characters have the intelligence to adapt to their environment and adapt themselves based on the reward they're getting back. And then finally, something a bit mundane but maybe more relevant to the audience in this room here, you can have automated code debugging and make our lives easier. Over the last few years, there's been a lot of advancements in deep learning, but then over the last couple of years, there have been a lot of advancements in reinforcement learning as well. So a great example of that is, DeepMind teaching AlphaGo how to learn how to play Go from scratch using deep learning and reinforcement learning. There are a couple of examples at Microsoft as well where we have deployed similar technologies and products, or our achievement with Miss Pacman that Tavian will talk about. But if you look at these individual successes, you might think that, wow, we've made a lot of advancements in RL and we're really close to solving this really, really hard problem, but that's not really the case. So this diagram, I think, does a really good job of explaining where we are today. So the white circle is all of the instances of RL problem that exist, or all of the real-world problems that we can model as an RL problem, which is quite a lot. And then the blue circle is, problem instances where we've had limited success, where we're hitting that ceiling or wall that we can't really push through today until we come up with new techniques. And then finally, you have this really small red circle where we've had really good success. We've built stable and efficient solutions. And a great example of this is Decision Service by Microsoft that leverages this ability to, where the agent only needs to worry about the next step and the next action it needs to take and the next reward it's going to get. So it's not really concerned about the long-term reward at this moment. If we could solve these problems, or even if we, our long-term goal at Microsoft or Microsoft Research Montreal at least, is to build a general purpose RL algorithm that can tackle much more complex tasks, it's much more sample efficient, and it's much more stable. And if we can solve these problems, then we can hopefully take that red circle and really try to expand it as much as possible. So I'm going to show you, this was just a quick intro to RL. I'm going to show you a quick video of the technology behind Miss Pacman, and then Tavian will walk you through, do a deep dive into the code itself.
Video games are one of the best ways to demonstrate advancements in AI, as they require human-like intelligence to perform well on them. Maluba has developed an advanced reinforcement learning algorithm that beat the Atari game Miss Pacman and achieved the maximum possible score of 999,990 points, surpassing the best human score by 4x. No human or AI has ever achieved this score because of the complexity of the game and availability of limited lives. We perform well on the game by breaking it into many small problems with a separate reinforcement learning agent for each problem. On screen, we have a total of 163 agents, 154 for pellets, 4 for ghosts, 4 more for edible ghosts, and 1 for the moving large fruit. Each agent also has its own reward function. We give a small reward for eating a pellet, a large reward for eating a fruit or a blue ghost, and a large negative reward if Miss Pacman gets eaten by a ghost. At each moment in time, all agents send their action preferences for the current game state to an aggregator, which selects the best action for Miss Pacman based on a weighted average of all preferences. By breaking up a problem in this way, it becomes easier to learn, as there are now many agents that learn many simple tasks instead of just one agent that needs to learn a very complex task. Here, the arrow represents the direction the agent wants Miss Pacman to move, and the size of the arrow shows the strength of its preference. The strength of the agent's action preferences are also visible on the heat map. Beyond Miss Pacman, this fundamental advancement in reinforcement learning can improve decision-making in complex settings, such as sales funnels, financial models, or robotics.
All right, so for the rest of the session, Tavian will walk you through hybrid reward architecture, which takes a really large complex problem and breaks it down into a lot of smaller problems. And then these agents individually work together to communicate to a higher level agent, which finally makes the decision. Tavian?
Thanks, Rahul. So yeah, my name is Tavian Barnes. I'm one of the engineers at Microsoft Research Montreal, formerly Maluba. And I worked a lot on this project, mostly towards the end when we were actually tackling Miss Pacman proper. But I'm actually going to walk you through basically the whole history of how we came at this problem initially, and over the course of a year and a half, we were able to make significant progress on it. So I'll start out with just a little bit of an introduction to our reinforcement learning team. At the time that we started working on these kind of tasks, there were only 2 people. So there was Harm and there was Mehdi, and there was an intern, Josh, who was with us for about a year. And we were really interested in scalability of reinforcement learning. So that means the ability of algorithms to tackle problems that are harder or bigger or have a larger state space or more complicated functions to learn. And the initial idea that the team came up with was something we called separation of concerns, or SOC. And we had good results on this with a few little toy games and problems that we gave it. And the idea was basically the fundamental CS idea of divide and conquer. So when you have a really hard problem, some game or other task that's very hard to learn, you might want to break it up into chunks somehow. And if each of these chunks is easier to learn and the solution to each of these chunks contributes to a solution to the overall task, then maybe you can make some headway there. And the SOC paper led into another paper, multi-advisor RL, and finally HRA, where we got our big results on the actual Miss Pacman game. But so to start out with SOC, the idea that this paper explored was looking at various ways that you can break down a single task that would normally be represented by a single agent and break it down into multiple agents and various architectures for doing that. So do you want the agents to be able to talk to each other, or do you want them all to output some sort of their own action and then pick the best one somehow from that? Or do you want them all to communicate with maybe like an advisory agent that takes input from all the other agents and determines which suggestion is the best. So this diagram sort of explains this, where there's a few different possibilities. In A, you have them all the agents communicating with each other and then outputting their own action preference that you select from. In B, the agents are still communicating with each other, but you sort of select one as the leader, and its action is ultimately the one that gets chosen in the environment. And then the last thing I talked about is C, where you have sort of an aggregator node or a head node that is taking all these suggestions from the other agents. And in this example, the agents are actually not communicating with each other. So they're just focused on their own subset of the problem. And then the aggregator has to learn how to determine whether the input from agent 1 or agent 2 or agent 3 is more important at any given time. And so there's various reasons that you might think that any of these approaches would do well. And depending on the task, they can. But we basically found that the architecture C, the one on the right, gives the best results. And there's a few reasons for this, and mostly they are to do with behavior that you see where each agent is only looking at maybe a subset of the problem, and sometimes because it's only seeing a subset of the problem, it thinks, well, in my subset, there's very obviously a best move, right? And if each of the agents has a different idea of what the best move is because its view is sort of myopic, then you can end up in this state where the agents sort of become attractors, where you may move towards the preferences of one agent and then suddenly start moving towards the preference of another agent, and then to the third agent, and then cycle back to the first agent, and you can sort of move around the map or whatever your environment looks like and not make any real progress because the agents collectively can't really decide on what to do. So that's the importance of sort of this aggregator. So you can see here we just have a few examples of some tasks that we applied this SOC model to. Pong on the right, and something that kind of resembles some of these old-fashioned video games. In the other cases, a simple little navigation task around a map with walls, and so we got some pretty good results. But these are not on production grade problems. These are on simple problems that we were experimenting with. So then our next step was basically to take the experimental results that we got with the SOC paper and come up with more of a theoretical underpinning for why those behaviors happen. So if you're interested in some of the theoretical or the mathematical insight behind the behavior of the different ways that you can do SOC, I highly recommend checking this paper out, the multi-advisor RL or MAD-RL paper. And we basically prove a few criteria on when you can expect these attractors to exist or not, and the kind of behaviors that you want from your individual agents when you are breaking one problem up to be solved by multiple agents. And so we started here with sort of a simulated game that we call Pac-Boy, or the fruit collection task. And the idea is to have a much more constrained game than the actual full game Miss Pacman, but it still resembles it, and basically all the behaviors that you might want to learn in the real game, we think you can try to learn in this game, but a bit quicker, but just because of the more constrained size. So the animation you're looking at here is actually what deep Q learning does on this game. So this isn't HRA yet. This is sort of like the conventional, state-of-the-art or standard baseline model that people use for tasks like this. And the interesting thing that we're illustrating here is now it kind of gets paralyzed and stuck in a corner, and it's too afraid of the other ghosts, the red dots that are moving around trying to eat it, to make any progress and actually complete the level. So that's a behavior that we've had to contend with and find ways to get around at various stages throughout this project. So we'll just keep that in mind for later. We'll come back to it. So I actually want to switch over for a minute, and I'm going to show, so you saw that there's a GitHub link here. And if you guys are interested at all, you can check this out. And I'm actually going to show you some of the stuff that you'll see in this repo. So if you want to reproduce any of the results that we had on these tasks, all the code is there for the Packboy task, and you can clone that onto your computer and try it out. So if I just switch over to my laptop for a second, I'll show you the Packboy game. So you can play it yourself. So here's sort of the very, very constrained model where there's no walls, and I can kind of just move around the map like this. There's also more complicated maps. So if I do this small as opposed to mini, then you'll get the map that we were kind of showing in the slides, and you can try that out. And so I actually trained an agent this morning just to double check that everything is still working the way that I expect it to on the small one. So I'll show you a demo of that running. So here is an agent that I trained with HRA this morning, attempting to just solve the very basic version of this fruit collection task. So that's pretty good. So I talked about a couple problems that we saw in our earlier experiments. So I talked about the attractor problem, where you can end up with sort of too many competing influences, and your overall agent can't decide what to do, how to balance these various inputs. There's also the problem of your agent being too fearful, so where it's afraid of the ghosts or any possible negative rewards, and that prevents it from actually completing the game, solving the level, collecting the final reward, because it's too afraid of dying. But there is a happy middle ground, and we found that middle ground finally after about a year of work, and we applied that to solving the harder problem of the actual Miss Pacman game. So here's the final paper, which was presented last December at NIPS. And this was a really big moment because it basically confirmed that all the work we were doing on these sort of scaled down problems, it actually does generalize to these bigger and harder scenarios. So why is Pacman important? Like, why specifically were we looking at this game? There'd been a lot of other work. So in the years before this, there was a work by DeepMind that had sort of one architecture that learned to solve a lot of these Atari games. So there's like an Atari benchmark set with a few games in it. And this one algorithm, this A3C algorithm, did pretty well on the collection of games, but some of the games it found harder and some of them it found easier. So I'm not sure how well everyone can see, but in this graph we sort of have a stack of which games the A3C did really well on at the top, and at the bottom, games that we didn't do very well on at all. And the line in the middle is sort of where the AI is at human parity or better than human parity in that experiment. And then everything below there is where the AI didn't reach human parity at playing these video games. And so, I mean, this is another example of where like RL is actually a hard task. And you'd think that maybe video games from the 70s and 80s would be something that we could just trivially solve, but it's not really the case. Some of these things are actually hard. And Miss Pacman is somewhere near the bottom. We're about fifth or sixth in the bottom there. So it really was not an easy thing to learn for the existing state of the art at that time. And so there's a few reasons that the game is hard. One is that just the state space is actually gigantic. Now, to a person, it sort of looks like a very simple game. But we have a lot of our own intrinsic biases in why we think that this is simple. It's hard for an AI to learn all the ways that we generalize, looking at this and coming up with like, oh, well, all the pellets are kind of the same, so I don't really need to know too much about the pellets separately. But the total state space is actually gigantic. It's bigger than chess. So you have to come up with some way to mitigate that. And the other problem is that the value function is not smooth. So there's states that may look very similar, but they have a very different expected reward. So a couple of situations that this can happen are things like where there's a threshold where a ghost may be too close to you and you can't run away. So if it's just over this threshold, you're going to lose the game. There's nothing you can really do. Whereas if it's just behind that threshold, then maybe you can do some nice maneuvers and escape from it. So these kind of very steep changes in the value function mean that it's hard to model it in a low-dimensional representation. It's hard to simplify that value function down to something that you can learn with a reasonably sized neural network. So we applied HRA. And HRA, in this case, is like an extreme amount of decomposition of the problem. It's an extreme amount of divide and conquer. So specifically what we had was we had one agent learning how to handle every sort of pellet-sized chunk on the map. So there's an agent voting for the best behavior kind of at every fixed position on the map that you might see, and then there's also agents that are sort of attached to the ghosts and one to the character itself that learn, the ghost agents hopefully learn that you should be avoiding the ghost, move in the other direction away from it, or away from where it's moving, that kind of thing. And then we learn all these agents separately, and we can combine their results into something that can actually beat the game. So I'm going to get a little bit technical, just because that's kind of a high-level overview of what HRA is about. So this is going to be a very low-level thing, but I'll try to connect it to real-world concept a little bit so you can follow, even if you're maybe not familiar with all the math behind reinforcement learning. So the standard setting for reinforcement learning in problems that are fully observable, so where you get to see the entire state the whole time, like most board games and, of course, most video games, is that you think that the underlying world you're trying to learn about is a Markov decision process. So you think that the underlying world is in a particular state, and you can know what that state is, and you can take actions in that state, and based on the actions you take, the world is going to transition into some new state. And the transitions that happen depend only on the current state that the world is in, and not necessarily on the history. Although if you have some sort of scenario where the history is important, you can maybe just model the history, the relevant parts of the history anyway, as part of the state. So it's a flexible enough representation to capture a lot of real-world problems. Everything from video games to like trying to train self-driving cars and stuff can be formulated in this way. So you have your state space that you call S. You have an action space that you call big A. And this is just the set of moves that you can take in your environment. So for video games, it's usually pretty straightforward. It's just all the directions your joystick can move and all the buttons that you can possibly press on your controller, this kind of thing. Or for a PC game, maybe all the ways you can move your mouse and all the keyboard keys. So in some of these cases, it can be fairly limited. In other cases, it can be, you have a very large action space, and you might want to decompose the action space itself. And so that's the area of some other approaches to scaling reinforcement learning is kind of on breaking down the action space. So options does that, for example. But we kind of focus on breaking down the state space, or actually, more accurately, we focus on breaking down the reward space. So we've talked about these positive and negative rewards, and that's kind of very key to reinforcement learning. And it's kind of how a lot of people think of how people learn, or how animals learn at least, where your child or your pet does something, and it's maybe going to get a positive reward, positive feedback, encouragement from you, or maybe it's going to get a negative reward. Maybe you're gonna say, hey, that was a bad thing to do, don't do that again. Or maybe it'll be some intrinsic negative reward, like it hurts itself and it learns not to do that kind of thing again, right? Another thing that sort of separates RL from other forms of machine learning is that you are working in a world that is changing all the time, right? So you don't get to look at a whole bunch of data ahead of time and try to learn off that. You have to operate in the real environment, and if there's something you need to learn from that environment, you have to do it quickly, because the worse you do in this environment, the worse off you are. So anyway, in the discrete case, we break down the problem into a series of time steps, and at every time step, you look at what the current state is, you decide on what action you want to take, and you get a reward back from the environment. So the environment reward function, Rn there, tells you, basically whether that was a good or a bad move. And the details of how that reward function behaves can be important because some rewards are much harder to learn than others. Sparse rewards are the hardest to learn, right? So that's where maybe you only get points after you complete a game and not for any of the individual subtasks. And if you can push some of those points sort of earlier so that when the agent does something that you think is probably a good thing for it to be doing, if you can get that reward earlier in the process, it becomes a lot easier to learn. So anyway, after you take an action in the space, you receive a reward. You also get to see what the next state is. And this can be non-deterministic. It can happen according to some probability distribution. Or you can have fully deterministic systems. And it happens that Miss Pacman actually is fully deterministic. So if you're in a given state, you know the position of everything, you can actually learn to predict what the next thing is going to be. We didn't happen to do that in this setting because we learned in a model-free way, but it is hypothetically possible. So anyway, couple more items of terminology. In reinforcement learning, you hear about policy functions a lot. So your policy is basically the ultimate thing that you're trying to learn in reinforcement learning. Your policy is given a state, what action should you take in that state? And you can have a deterministic policy where it always is just selecting one action. But in the more general case, you can learn a probability distribution over your actions in any given state. So you can say, oh, I think there's a 90% chance that we should take this action, and maybe a 10% chance that we should take this action that I think is maybe slightly worse, and then I'll assign 0 or 0.01% or something to the other actions that I think are pretty bad in this state. And you want to find a policy that's good in a particular way, and the way that's usually written is you want to maximize the discounted sum of rewards over time. So that's the infinite sum of the rewards that you get at every time step, and you have that the gamma to the I in there, which is basically a discount factor that controls how important it is to get rewards now versus getting rewards later. So as you go further and further into that sum, gamma between 0 and 1 will get smaller and smaller. So if you have gamma close to 1, then long-term rewards can be maybe sort of close to as important as short-term rewards. Whereas if it's small, then you're really maximizing for your sort of immediate gains. All right, so just a little bit more technical stuff. One extremely popular way to do reinforcement learning is called Q-learning. And in Q-learning, what we're trying to do is we're trying to basically learn to estimate that sum that I had on the previous slide. You want to learn a quality function for your policy that says, given that I'm acting with respect to this particular policy, and I'm in the state, and I'm going to take this action, what is my expected total reward over the rest of the future acting according to this policy? And so whatever action that happens to, in any given state, whatever action happens to maximize your Q function is going to be sort of your best action. So that's like if I take this action now and then I follow this policy for the rest of the game, what's my expected score, or what's my expected total reward? And there's a lot of different Q functions corresponding to the vast array of different policies that you can have. And because there's a bunch of them, one of them has to be the best, right? So we call that one Q star, and that's the optimal quality function. And so we're just maximizing over all possible policies and trying to learn, if I took any policy, what's the best that I could do in this scenario? And if you can learn to compute Q star, then you can sort of go backwards from that and determine what the actual best policy is. Because the best policy is going to be selecting greedily the best action at every state according to Q star. So if you have a good representation or a tight enough approximation of Q star for your real environment reward, then just greedily selecting the best action at every step will get you the optimal policy pi. And I say here that this solves the RL problem in a model-free way. So there's a difference between model-based methods, which are methods that try to learn the underlying Markov decision process that we think is representing the environment. But there's also model-free problems or model-free solutions where we don't actually learn anything or very much about the underlying MDP. We just learn how to take good actions with respect to that MDP. So it's a little bit less to learn because you don't have to really figure out the details of how the world actually works. You just have to figure out, okay, what's a good policy for taking actions in this world? How can I do well? So with that, we get into the actual definition of HRA. So Q star can be a very complicated function. And it's not always easy to learn, even with something as powerful as deep networks. So we want to chunk it. We want to break it down. And the way that we do this is we say, okay, the reward signal can have a lot of different parts to it, different components. And sometimes it's obvious how to break this down. And so in a game like Miss Pacman, it's fairly obvious where your reward signal can come from a lot of different parts in the game. So every time you eat a pellet, you get a certain number of points. Right, so that's a lot of different components already. If there's something like 160 pellets, then each of those is a separate way that you can get a reward. So that's a separate component of your reward function. You can also die by getting attacked by a ghost. And so that's another way that your reward can be assigned to you is through the ghosts. And the ghosts are sort of independent of the pellets. Right? So the ghosts follow you around the map, and your interactions with the pellets don't really control whether or not you're going to get eaten by a ghost. So it's a nice separation, fairly clean. And there's also a few other components like the big fruits that give you bonus points, and there's the special pellets, the power pellets that let you start eating the ghosts. So that's how we broke down Pacman specifically, but in the general case, HRA is just taking any way of decomposing the reward function at all. And some will be better than others, but to formulate it, we just take any way of decomposing it into a weighted sum of components. And then you do the same thing to the quality function that I talked about previously. So instead of having one Q function that tries to estimate your total reward based on a particular policy, you try to have a bunch of independent Q functions that try to estimate just the total reward according to that component, the corresponding component of the reward. And then you add them all up with the same weights as you did the reward, the environment reward, and that gets you the Q sub HRA function. Now, why does this help? Well, basically, if you've simplified the problem at all with this decomposition, if each reward component is, maybe it depends on a smaller amount of the state space, or maybe it depends on the state space in a simpler way, maybe a linear way as opposed to a nonlinear way, et cetera, then each Q function, each Q component function can be easier to learn. And optimizing the sum of all these component Q functions doesn't actually necessarily converge to the optimal policy with respect to the environment, but it basically gets you fairly close in a lot of scenarios. And because it's learning so much faster, it's sort of better than doing it in a way that would theoretically eventually learn, because you can learn now, and you can learn a policy that is way better than you can possibly learn according to traditional Q learning over any time scale. And it also is the case that if you have a particular policy, so once you've decided on a policy, your Q function for HRA is the same as the environment Q function for that policy, and that just comes from the linearity of expectation in the definition of the Q function. All right, so that's all the math. Now let's get into some of the results that we got on the game itself. So we did all this complicated stuff. We broke the problem down. There's a lot of extra information that we're providing, segmenting the game state into all these individual components. Each of the separate pellets is fed to it separately, each of the positions of the ghost and the character and all this stuff. And we still didn't really do that well. So you can see that we kind of hover somewhere around, we're above 0, but we're not even at 1,000 points really, and we kind of plateau at that point. And what's happening there is that we're a little bit too afraid to try new things. So we basically think that we've solved it, even though we haven't. We think that, this is about as good as I can do. I'm not going to try new scenarios. I'm not going to try to start the game any differently than I did the last time because I know I can get at least this many points this time. So a little tweak to control for that, which we called safe random start. And so in here, actually, we just added another reward component function that's actually literally just a random number. It's just assigning random weights to all the possible actions in every state. There's pretty constrained. So we're not trying to, if we think the rest of the system has learned good things to do, we're not trying to override that with a random result. But near the beginning where we don't really know what the best course of action is, this is helping us generalize, or is helping us explore, and it's helping us learn quite a bit better. So we do the safe random start, and suddenly we're getting around 10,000 or plateauing maybe around 8,000 or 9,000 points on the game, which is cool, but it's not really enough. So the next thing we did is we applied a certain amount of normalization. So one of the problems that we talked about before was this issue of when you reach near the end of a level, the agent becomes too afraid of the ghosts to make the necessary progress to actually complete the level. And this is sort of a tough problem because at the beginning of the game, you don't want each pellet to have too much influence over the agent's behavior because there's so many more pellets than ghosts, right? So those weights need to be tuned so that at the beginning of a level, it's not, it fears the ghosts appropriately and doesn't do things that are too dangerous. But once you reach the end of the game, now suddenly, the signal coming from the pellets is not strong enough to overpower the fear of the ghost because you only have 2 or 3 pellets left, or 5 or 10. And with the way that the weights were, at the start of the level, it's not really conducive to actually trying to, dodge the ghosts and find those pellets to complete the level. So we applied normalization where we put the ghosts at a separate level. So the total influence of the ghosts and the total influence of how the pellets, however many pellets are left, stays roughly constant throughout the progression of the level. And that lets us do a little bit better. So you can see here that that we eventually, get 3,000 or 4,000 more points than if we were just doing, the non-normalized way with the safe random start. And it looks like from this graph actually that the previous line, the orange line, initially learns faster and then kind of plateaus, whereas the green takes longer to learn, but eventually learns better. That's not really the case. It's a little bit misleading because the x-axis is games played or levels completed basically, and the orange line is spending so much more time on every level because it's so afraid to actually go out and get pellets that if you looked at like the number of frames that you've taken, we're able to learn way quicker with this green line. And the last thing that we did was we incentivized exploration a little bit. So this basically involves adding another agent that estimates a somewhat strong reward for situations that it hasn't seen before. And this leads it to a little bit more exploratory behavior. If it sees something that, I've never tried doing this particular move, or I've never tried, maybe like taking that loop off the edge and coming back, it's going to try to do that and learn what happens. And by exploring more of the state space, you can, of course, find ways to do better at the game. And so when you do more exploration, It can be riskier, but you can also be rewarded by finding better paths of play, better policies, and better actions. And in this case, yeah, we did significantly better once we added this dedicated exploration as well. So by the time we play 1,000 games or so, we're up to something like 16,000 points. And if we keep going, we get up to somewhere around 25,000 points before we hit what we think of as a plateau. So here on this graph, we're comparing against A3C. That's the standard kind of benchmark or baseline approach to games like this, asynchronous advantage actor critic. And so there's two separate lines for A3C. There's A3C pixels, which is the red line, and so that's the traditional A3C approach where you just feed it each frame, the frame images of the game one after the other, and it learns how to play based on that and the signal coming from the ultimate score. And then there's A3C channels, which is basically our attempt to get a little bit more of a fair comparison with HRA. So because we did all this pre-processing on the input signal, chopping it up into these chunks and letting it know explicitly, these are the positions of the ghosts and this is the position of Pacman, this kind of thing. We wanted, for a fair comparison, to provide that to A3C as well. And you'd think that this extra information would be able to make it do better. And it does do slightly better, but it's basically within about the same range. So maybe somewhere around 2,000 or 2,500 points that it kind of plateaus at. And you can see it's still sort of jumping around. It hasn't really converged on any particularly great line of play. And so that's pretty interesting. So that sort of signifies to us that the hard part of solving games like this is not learning how to interpret the images or learn how to interpret the video and stuff like that. The hard part is really, once you can interpret that signal, how to represent the state space and the rewards in an effective way that you can actually learn. And even breaking the problem up like that is still, your problem is still very complicated, and A3C basically can't learn it to nearly the same degree that we can by applying HRA. So I'll show you the numbers in a little bit more detail. So here's how we compare to what at the time were all the major results on this game with various methods. So human is at the top, so that's not like the best human score ever, but that's like an average competent human at the video game can get somewhere around 15,000 points. If you behave completely randomly, you don't do very well. You get maybe a few hundred points. And you actually see on this table that there's two evaluation metrics. So there's fixed start and random start. So because Miss Pacman is a deterministic game, there's a lot of memorization that you can do. Right, so once you've seen a scenario in a level, you can kind of memorize, I should do this in this scenario and do pretty well. So you see that a lot of these methods, they can do very well in this fixed start scenario because they can basically memorize how to play certain lines of the game. If you feed them a random start, which is actually just accomplished by doing a few random actions at the beginning of the game before you hand control over to the agent, so that randomizes the position that it's starting from. You see that most of these methods pretty much fail to generalize. They'll do maybe half or a third as well as they do in the fixed start scenario. Whereas if you look at the very bottom row, not only is HRA actually beating the score of all these other methods, but we're extremely similar performance between the fixed start and the random start. So we think that this means that we've successfully learned to generalize in a way that other methods haven't on these games. And so that's cool. We beat human performance, and we beat all the other algorithm performance, but it's not 1,000,000 points, right? So there's one more thing that we did to get to 1,000,000, and that's something that we called executive memory. So the analogy that I like to use for this is if you play a video game a lot, eventually, certain tricks and things will get committed to muscle memory, you might say, right? Where you've seen the scenario before and you know that, I just hit left and A or something really quickly and I can do this jump, or you memorize exactly how to get the double jumps and everything becomes second nature, right? So For the fixed start case, there's a lot of opportunity to do this. And you could try to memorize, once you learn how to beat a level, you can memorize, hey, if I'm going to play the game again, next time I see this level, I know that this sequence of actions was good. I know that if I've ever seen this particular state before and I made this move, I didn't die at the end of the level. So the executive memory agent that we added basically remembers any actions that you take in a level that ultimately result in you not dying in that level. And then the next time you play that level, or the next time you see any of those states that it's seen before, it assigns a strong positive reward to playing those actions in those particular states that it knows could lead you out of that level successfully. So when you do this, you don't generalize as well, or you basically don't generalize at all, because in a random start situation, you don't expect to see exactly the same state very often. But in the fixed start metric, it basically lets you do extremely well. And you can see that we pretty much never stop learning. There's no plateau. We're able to get to extremely high levels in the game, and we're able to get to an extremely high point total. So somewhere around 270, 280,000 is the best human high score ever on this game. And if we play somewhere around 2,100 times, we beat that, and we're still shooting up. And we actually get all the way to 1,000,000 points, or 1,000,000 minus 10, and the score counter rolls over at that point. So we pretty much, that's as good as you can do. And if you want to see the moment where that first happened, here it is.
0.
So it's a little bit small, but you can see the score counter is somewhere 99999, and it rolls back over to 0. So that was a cool moment for us. As soon as we saw that, we basically knew that a lot of the work that we were doing over the past year had paid off, and we had a new algorithm and a new method that was able to solve previously unsolved problems and do it in somewhat dramatic fashion. So I hope you've enjoyed this presentation. I hope you're a little bit more illuminated about hybrid reward architecture and the various approaches that we took to arrive there, and about reinforcement learning in general and how cool of a space it is and the progress that we hope to make in the future. So with that in mind, I'd like to open it up for questions. Thank you very much. Yes?
So you've reached the maximum score, but do you see an improvement in the amount of gates? Did you get to that point?
So the question is, we reached the maximum score, but have we done more work to see if we could get to that point faster, or further improve the efficiency? And the answer is, I don't think we really have explored that too much. There's probably a lot of a few more tricks that we could do, but we basically wanted to do as little work as possible. Right, like as little hand tuning of everything. So there's maybe some extra tweaks that we could apply that would get us there. But the only way that we're going to get there significantly faster is some even newer, more fundamental RL algorithm. So we sort of think about these things. But yeah. Yes.
Well, now that you've beat this Pacman, are you looking for ways to generalize solution for developers that apply?
Yeah, we were thinking about that a little bit. So like I said, the code is on GitHub, and you can take that, and it implements a lot of variations of HRA, and so you can plug your own problem into that and try tabular HRA or HRA with generalized value functions, HRA with deep Q networks or without. Yeah, so that's sort of the level at which we've made that available.
Do you think executive memory has any relationship to like transfer
So the question is, do I think executive memory has any relationship to transfer learning? By the way, if you feel like coming up and using the microphone for these, then the recording will catch them a little bit better and I won't have to repeat everything. It's up to you. If you're in the front, don't necessarily bother. So transfer learning, it sort of has a relationship in that it makes transfer learning harder. The executive memory relies on basically hashing the state and seeing exactly, if I've seen this state before, I know what to do. So it decreases generalization and your ability to transfer that knowledge over a little bit. Actually, yeah, applying or being able to do transfer learning with respect to HRA is another area that might be interesting for research because with the way that you decompose a problem, that may be harder to generalize across problems. So the exact decomposition you use for something like Pacman is probably not going to make sense for any of the other Atari games. And so it's even harder to sort of like share something like weights or share knowledge across. But it's an interesting area.
Sorry. I was curious if while you were programming the game and it was getting better and better, did it ever play in an alien way that humans don't normally play? Like for instance, the AlphaGo, and I'm just parroting back what I read. I don't really understand how it worked, but was playing Go in a way that no human had ever played before. And I guess that the champion Go master actually studied some of that, and he started using it against other humans, and he started winning, right? Did you notice any of that kind of behavior? When you get to 500,000, you're already twice as good as a human. Is it just going faster, or is it actually?
No, that's a very good question, and you're right. A lot of the new strategies that were pretty much invented by AlphaGo were very fun to watch, and it was very cool to see like a computer come up with new ways to play a game that's old like that. Now, I will say I don't think that Miss Pacman has kind of like as deep a strategy as you can have in Go. So even though it's got on the face of it, it's got a somewhat larger state space, or probably comparable. I actually don't know the numbers off the top of my head. There's not an excessive amount of like strategy you can learn. So the most alien thing that you'll sort of see it do is it just has way better reflexes than people do. So once you see the higher levels, the game is moving incredibly fast, and HRA has no problem keeping up, whereas a human would be pretty quickly overwhelmed. But you do see occasionally behaviors that you might consider weird, and I'm not even sure that these are optimal, but they're definitely good enough to get to a high score. But sometimes you'll see it sort of looks like it's on some particular path. Maybe it's trying to get to the power pellet in the corner, and then it'll just suddenly decide not to. And I'm not sure exactly why it does that. Maybe the ghosts move in a certain way, and it realizes, oh, I can't really make it there anymore. I got to do something else, or maybe it's sort of a horizon effect where it sees like, now that I'm this close, I'm observing something that I didn't observe before. The weights have changed, and I realize that that's not actually my best course of action. So, yeah, it's tough to say. I don't think we've done any like deep analysis of the ways that it actually plays the game. But good question. Thank you.
So you said that you added an agent to incentivize exploration.
Yes.
And that when it had seen a position that it had seen before, then it might try to do something else differently this time. But if the state space is so huge, how are you recognizing that this is a place that I've seen before? Is it actually just, oh, here is this one in 10 to the 50th states, here's another of these 10 to the 50th states?
Yeah, so as far as I know, I'd have to double check the implementation exactly, but my understanding is that it's basically only useful near the beginning of a level, where there's only a few states that you can kind of possibly be in, and that after a while, there's kind of too many states and everything is going to be exploratory. So it's sort of trying to incentivize early exploration just by doing that.
Yeah, you talked earlier about how you added a randomization agent,
Yep.
but then later on through your path of kind of exploring and learning how to make this thing better, you added agents like he mentioned for exploration and normalization. Did you ever go back and try removing the randomization agent to see if that made an improvement or if it was still necessary once you'd kind of introduced some randomization via the other three agents?
I'm not sure. We probably did, and my guess about what would happen is that once you have the model has a fairly good understanding of the mechanics in the beginning of the level, then all of the predictions that it makes are strong enough to sort of overpower that random agent suggestions. So I think eventually after you do a certain amount of training, if you remove the random agent, you're not really going to see any difference in behavior because we're more confident in the other agents are more confident in their decisions.
So it seems like one of the major magic ingredients that kind of brought everything together for you on top of everything else was adding that executive memory. Is that something like a solution that you had kind of prepared really early on in your research to maybe add in, or is it something that you more came up on the fly when you encountered kind of problems like breaking these scores? And do you have any insights on why that might have been so successful for this sort of game?
Yep. Yeah, so we added it fairly late, actually. So in terms of the progression of the slides, that kind of corresponds to the progression of reality, where we had that 25,000 score, and we were looking at, okay, how do we break this plateau? What ideas can we take advantage of, and to do that. So in terms of why executive memory really helps, it's basically just primarily due to how deterministic the game is, and the fact that if you learn a trajectory that will beat a level, then you may not necessarily have learned the best one, but if it happens in a reasonable amount of time, then you can spend more effort learning how to beat the higher levels. So the tractability goes way up, because once a level is solved well enough, you can spend suddenly you're spending 90% of your time learning how to solve the next level. And then once you learn that, you spend most of your time learning how to solve the next level, and so on. Whereas without it, you kind of are spending a little bit more effort on the earlier levels that you've already seen before. Just sort of you have to do more effort to play through them well, and to make sure that you're not falling into traps and stuff. So.
In my limited experience in RL problems, there seems to be a bit of an art to it.
Yeah.
Could you just describe how you would think about generally approaching a problem and breaking it down using HRA, as far as how do you divide the agents and such?
Yep.
Yeah, just in a general
Sure.
sense.
No, you're definitely right that the HRA is there's a little bit of an art. That the reinforcement learning is a bit of an art in general. We still struggle with stability a lot, which means you may train using some algorithm once, and it may work, and then you use a different seed the next time, and it may not work. And you don't really see that in traditional deep learning, where you can start from any random place and always converge. So yeah, RL is a little bit harder in this way. Is a little bit more unstable. So in terms of my advice in applying something like HRA or any of these hierarchical decompositions of the RL problem in general is, well, first of all, you don't have to go as crazy as we did. So even if you just decompose your reward signal into maybe 2 or 3 components, that's still an exponential savings in terms of the complexity of the actual Q functions that you can that you're trying to learn. So even if you have a problem where the reward really comes from 2 different parts of the system, even just doing that breakdown can be enough to provide a tremendous amount of benefit. And the other thing is just be smart about how you do the decomposition. So there's almost an infinite number of ways that you can break apart any reward function into a sum of other reward functions. But the best ways to do it are ways where each component is similar, or is simpler rather, in a particular way. So it depends on less of the state, or it depends on the state in a simpler way, or it's somehow isolated from the rest. And so if you just break it up in a random way, you probably don't make it any more tractable. So there has to be a little bit of thought there. Now, eventually, we would love to be in a situation where we can automatically discover these ways of partitioning the problem. But for now, yeah, let's do it by hand.
Can you use HRA to problems where the evaluation function is some real-world process, so you need to minimize the number of epochs, you cannot run it so much times, or is it not suited to this kind of problems?
So that's a very good question. And I would say that for a lot of real-world problems that we're dealing with now, just HRA will not really be enough to save you. And we actually are doing a lot of active research in this area as well at MSR Montreal, and we're calling it safe reinforcement learning. So in other words, we don't trying to avoid doing dangerous things in real environments where that might penalize you. So obviously self-driving cars are like a big example of this, but also we're ultimately trying to apply RL to dialogue. And so while you might learn a lot if you sort of like make up a random sentence that doesn't make any sense, you might learn that, okay, that didn't make any sense. It's a real negative experience for an actual human user if you go out and do that. So there's various ways that you can try to do safe exploration and also off-policy learning, which means like learning from examples where you've already acted in a certain way and trying to learn as much as you can from those without actually, regardless of whether those follow your current policy at any given time.
So you mentioned that it took you guys a year to go from the point where you could avoid the misfaction getting stuck in a corner to finally finding that balance between knowing to go after the pellet and make progress, even though it would put it closer to the ghost. Why did you guys avoid just touching the reward function and just saying hey, just tweak up the reward of the pellets to go higher and or the distant the fear of the ghosts to go down?
Yeah, because we sort of felt like that would be cheating a little bit.
Okay.
People will call that reward hacking or various other things. Where you're sort of trying to tweak the reward itself. Now, a certain amount of that I think can be good, but we really wanted to approach it from sort of a more fundamental level and really get a theoretical understanding of why do these behaviors happen and how can we ensure from a theoretical standpoint that we're not going to run into these situations rather than just, there's certain things you can tweak. So for example, you can, we have a little theorem that says you can always tweak that gamma parameter in the discounted reward sum to avoid having attractors. But we'd rather have an algorithm that can learn regardless of how you set your gamma so that you can use it for what it's designed to be used for. Right?
Thank you.
You're welcome.
How important to the agent was the actual layout of the maze? If you gave it a random one each time, would it just be lost, or did that factor into it?
That's a good question. There's only 4 different mazes or maps in Miss Pacman, the Atari version anyway. It does basically learn them all. So you can definitely see that once it has solved level 1 pretty well, its performance in level 2 is not going to be as good until it also learns that map. So there's an amount of generalization, but there's also an amount of it having to explore and do different things on different maps, different mazes. Now, I think maybe part of that is sort of from the way that we pose the problem. So we actually are doing things like dynamically discovering the new agents that correspond to the pellets, like when they get eaten, right? So when it sees a new map for the first time, it really has a lot less knowledge about it than like a person looking at it would. And we force it to learn the maps through exploration. So potentially, if we didn't do as much of that, maybe we could do better in terms of generalization. But for this game, we didn't really have to just because of the limited number of maps. Thanks.
I think you mentioned earlier in the talk that you were avoiding games, and that's why you picked Miss Pacman, that didn't have history. Maybe I misunderstood that there wasn't like a historical component, or maybe it was the Markov chain. You're staring at me like I'm a crazy person, so I must have missed a bunch of things. I was thinking like a game like Jenga or something, where each brick is pushed out there's a historical, thing to win the game.
Right. Okay. Yeah. So when if you're
Am I
thinking about when I
making
was
myself
talking
clear?
about modeling the world as MDPs, and how you need to be in a situation where the behavior given the current state in an action is totally independent. It's like
what-
conditionally independent of the history.
Gotcha.
But a lot of things are like this, even if you don't expect them to be. So if you think of something like Jenga, it doesn't really matter what sequence of moves were made to get the tower in a particular state. Like if you can look at exactly what the state of the tower is, you can basically simulate the physics of it, something like that.
So do something.
So a lot of games will have this property, and you can almost always formulate it in this property by sort of like cheating and just adding the history as a part of your current state if you have to.
Okay. And then the last question is, would you recommend any books or articles or something to learn more about reinforcement learning?
Yes. So actually, there's
For
a
someone
book
who
by
does-
Richard Sutton that's sort of, I think it's just called like Introduction to Reinforcement Learning.
Okay.
That's probably where I'd recommend starting. If you come up to me later, I can pull up some other examples from
Okay.
our, and yeah, I think Microsoft may have some informative resources online and stuff as well. So.
Okay. Great. Thanks.
Thank you. All right, any other questions? Well then, thank you everybody very much for paying attention to the presentation. It was great.